In this video, we're going to extend the ideas that we've learned about refraction and talk about something called total internal reflection and the critical angle. Now, what you're looking at in front of you is a semicircular glass block and a beam of light being directed from below, and the black dotted line is the normal. And as we've already seen with refraction, when light travels along the normal, it slows down but without a change in direction. Now, if I rotate the glass block slightly, you will see that the light still enters the curved surface of the glass block along the normal, so it carries on straight through, and you've got that angle of incidence being shown, and when it hits the far flat surface of the glass block, it refracts and it's bending away from the normal. And I know this because the angle of refraction is bigger than the angle of incidence. And that's really consistent, isn't it, with going from a high refractive index material, which is the glass block, back into air, which has the lower refractive index. Now, as I keep rotating the glass block, you'll notice that the ray of light is getting further and further away from the normal. And at some point, if I can just stop it in time, okay, there is that switching over between refraction and now reflection. Refraction and now reflection. And we're going to give this effect a name. We're going to call it total internal reflection. Total because it's complete reflection, internal because it's happening inside the material. And if you recall from your GCSE knowledge, the angle of incidence and the angle of reflection should always be equal, and that's shown on this animation. Now, just to give you the full picture, if I just return this back to how it was before, and I'm just going to turn on the reflections, because in reality, there are reflections of light from each boundary. And as I move the glass block, you can see that. Okay, those reflected beams are quite faint compared to the main refracted ray. But just have a look at how the intensity of the lower reflected ray changes as I increase the angle. Okay, the intensity is increasing. That red line is getting darker and darker. And then at that point there, we get that internal reflection. Okay. Let's have a little look at how the refractive index of the glass block determines whether or not we get internal reflection or we get refraction. So I'm just going to draw a diagram of that semicircular glass block, and we're going to locate our normal. And I'm going to shine light in at the point where we had that swapping over from refraction to internal reflection. And that means that this ray of light, which I'm now going to just highlight in red, is kind of skimming along the back surface of that glass block. I'm going to give this angle a specific name. Okay, I'm going to call it the critical angle. And the critical angle tells you when refraction stops and internal reflection begins. Now, the significant bit is this angle here. The angle of refraction is 90 degrees at the critical angle. And I'm going to assume that this is air. I'm going to call that N2. And this is the glass block, okay, material N1. So I'm going to apply Snell's law. N1 sine theta 1 is N2 sine theta 2. N1 is the material of the block. Sine theta 1. That is the sine of the critical angle. And that's equal to N2. Now, N2 is air. And we know that the refractive index of air is 1. Sine theta 2 is the sine of, that's a 90-degree angle. And you may recall that the sine of 90 is equal to 1. So in other words, rearranging this, the refractive index of the material is 1 divided by sine C. Okay, so there is that inverse relationship between the refractive index of the material and the sine of the critical angle. So we could do an example then. Let's imagine that we've got a glass block and it's got a refractive index of 1.5, and I want to know what that critical angle is going to be. So if I rearrange the equation, sine c is equal to 1 over n, and I want to know the critical angle, so that's sine to the minus 1 of 1 divided by 1.5, and you can check that for yourself, 42 degrees. So in other words, if I have this glass block with a refractive index of 1.5 and I shine light in at an angle of incidence of 42 degrees, then that is the point that internal reflection will occur. If I shine light in at an angle greater than the critical angle, internal reflection continues. Now, the important point about the formula that I've just derived for you here is it's only for an air boundary. So in other words, if we're going from glass or plastic into air, this equation works, but we'll look at an example a bit later for when we're going from one material into another. Okay, let's have a look at some applications then of this critical angle and total internal reflection. So diamonds, why do they sparkle? Well, it's all about internal reflection. Jewelers work incredibly hard to get all of the angles right within a diamond to ensure that light is internally reflected back into our eyes and not refracted. And if I just scroll forward here, you can see those exact angles that we have to achieve in order for that to occur. So what you're trying to achieve with the diamond shape then, there's your eye, and here is a source of light such as the sun. Okay, we want as much of that light to be reflected back into our eye again. Okay, we don't want light to be refracted out of the sides of the diamond. Now, diamond happens to have a very high refractive index, and that means that it's got a very low value of critical angle, which means lots of the light gets reflected back into our eyes again. An application that you're very familiar with, data transmission. These tiny fibre optic cables, these glass fibre cables, which probably run to your street, into some homes and businesses and connecting countries. And you can see the little graphic there. There are literally hundreds of these fibre optics connecting up all of the countries. And this is what we use to transmit data, our internet, our broadband data. So those of you who are familiar with kind of how computers work, we send pulses of light. Light pulse equals a 1, and the light being off equals a 0. So we've got those zeros and ones, we've got that data being sent along the fibre, and we use the principles of total internal reflection to send this data over huge distances. A medical example, endoscopy or an endoscope is to see inside the body. Endo as in inside, scope to see. So I've had one of these done, pretty painless kind of procedure. You have two different fibres. One of them sends light into your body and the other takes that reflected light and allows the consultant to see what's happening inside of you. So there's a little picture or two pictures of what might be happening. So obviously it's quite dark inside your stomach. So we have a light bulb and we send that light down the fibre using total internal reflection. That light then reflects off the inside of our stomach and returns up a separate fibre, and then that consultant can see exactly what's happening inside the body. So when we are laying fibres to send data across the world, we generally clad them. In other words, we cover them in a different material. And the question is why we do that. Part of the reason is to protect the fibre. The fibre is made out of glass, and to protect it into some kind of rubber coating obviously means that it's less likely to break or to get damaged. But there's more to it than that. It's about this critical angle. So here is my fibre. And let's imagine that the fibre is just surrounded by air. In other words, we haven't surrounded it by any cladding. So the core has a refractive index of 1.55. We can use Snell's law to work out what this critical angle is going to be. So there's my normal, there's my angle of instance. I need it to totally internally reflect. So in other words, I need this angle to be C or greater than C. Okay. At the critical angle, the light is skimming along this back surface of the fibre. Okay, so in other words, that angle there is 90 degrees. That angle there is the critical angle, and all I've got to do is to make sure that the light enters the fibre at or greater than that critical angle. So I can use the equation I've just derived to work out what that critical angle is going to be. N is 1 over sine C, and it's similar calculation to what we've done before. Critical angle is sine to the minus 1 of 1 over n, which is sine to the minus 1 of 1 over 1.55, and it gives you a critical angle of about 40 degrees. So in other words, if I shine light into that fibre at or above 40 degrees, then total internal reflection will occur. Now, what's really important here is that we are going from a high refractive index, which is the material that makes the glass fibre, into a low refractive index, which is air. And it has to be that way round. And the reason for that is we need this ray of light to bend away from the normal and not towards it. And you know from your work on refraction earlier that the way that we get light to bend away from the normal is we have to go from a higher to a lower refractive index. Okay, so you will never have fibres which have a cladding of a greater refractive index than the core. But let's have a little look at the effect then of putting cladding around the outside of the core. So we've got our core with a refractive index of 1.55. We've got that lower refractive index of cladding at n equals 1.45. Now, we cannot use the equation that we've used earlier. Okay, that is not going to work for us here because that was based on going from a material into air, and air has a refractive index of 1. We're going from one material into another. So we have to use the full form of Snell's law. So n1 sine theta 1 is n2 sine theta 2. N1 is 1.55. And we are sending light in at the critical angle in such a way that theta 2 is 90 degrees. Okay, so at the critical angle, theta 2 is 90 degrees. So I know that the sine of 90 is equal to 1, and so I can work at the critical angle as being sine to the minus 1 of 1.45 divided by 1.55. And when I do that, I get a different value of critical angle. So in other words, putting cladding around the core has increased the critical angle. In other words, I need to send light in at a greater angle than I would have done had there been no cladding. Just a little note before we move on from this. This fraction here must be less than 1. Okay, the maximum value of the sine of an angle is 1. Obviously, the sine function varies between 0 and 1. Okay, you have to make sure that that fraction gives you a value less than 1. Okay, otherwise you can't do the calculation or return a maths error on your calculator. So what's the benefit then of having a larger critical angle for our glass fibre? It means that light travels in a more direct path. So if I draw the fibre again without the cladding, we saw that the critical angle was 40 degrees. In other words, it's going to follow a path something like that. However, with the cladding, the critical angle is now bigger. I have to send it in at 69 degrees. Okay, you can see between those two diagrams, there's fewer reflections here than compared with the air. Okay, so that means light is traveling a more direct path, and it means it arrives at its destination sooner. But looking at the diagram on the left, you can also see there's some kind of spreading out of the beams of light. So this is directed in at 69 degrees. I could direct in at 70, 71. All of those are going to internally reflect. And what you get is a little bit of spreading out of the signal. Okay, so we want to minimize that. And again, increasing the critical angle to a higher value means that we get less spreading out of the signal because the rays of light follow a more similar path.